So now, this idea of Schrodinger's equation also leads to a couple other situations that we should talk about, and that's energy states. So a classic example to talk about energy states associated with particles. Remember, we start talking about orbitals, and orbitals change energy states and stuff like that. A simplified way of doing this is what we call the infinite square law. Okay? And the infinite square law allows me to describe wave functions of particles in a discrete amount of space. Cool? So in the infinite square law, I've already drawn I have drawn a few waves. You can see here what I call E equals 1. E equals 1. I have a half a wave. I have this part of the wave, and then it would come back and do this. Okay? So I have a half a wave going on here. Okay? The important thing about drawing these waves in the square law is that the initial position and the final position have to be at the same height. We call that the energy state. Okay? It turns out that energy state is going to be p squared divided by 2n. And then you can do substitutions of p to talk about Planck lengths. And the second possible state is a complete wave, one complete wave. Okay? Cool? And then the third is 1 and 1/2. So you can see that there's a relationship. The first one is 1/2 of a wave, 1 and 1/2. You can imagine the second system is going to look something like 1 wave, 2 waves, and 1 plus group. Going to look like here's 1 wave, 2 waves, that's going to be E4, it's going to be 2, on and on and on and on, so that it starts and stops at the same position. Okay, so that's the wave that gets into there. But when dealing with Schrodinger's equation, it turns out that the square gives me the value. We have a sine function in the Schrodinger's equation, but it turns out to be, when we're describing position, when we're describing energy, when we're describing about all these functions, it's the square that's associated. Okay, so E1 looks like the square of the signal up of a wave, which isn't all that hard to describe. It's just slightly more bulge square. Okay, so that's E1. That's the energy associated with that wave. That turns out to be p squared over 2m. Okay, typical energy equation by using momentum. We could do the exact same thing for E2. Just erase this one. And it's going to be, well, if it was like this, but when I square it, I bring up the negative values. The energy of that E2 wave is going to look something like this. And that is going to go back down to 0. Okay? And again, the equation for that is momentum over 2m. But this has now gone up to twice the energy. So it's going to be this 2m, but it's going to be twice the original. Okay? Which means there's going to be an energy associated from that. Cool? Moving on to the next one. We've got the 3. So it's going to look kind of like a weird camel. Goes up, down, so it's going to go up, and back. But the important thing is I'm not doing a very good job of that, is that these values are not allowed to go lower than that energy. Okay? So then you're dealing with E equals 3, P squared 2m, and then on and on and on and on. Okay? So Schrodinger was able to describe the energy by the way it would look like this, and these are the probabilities of the energy states. Which that object is going to be. So you can see as the energy increases, the behavior of that wave drastically changes. Okay? So that's energy states and applying Schrodinger's equation to it.